Hi, so this is another video, and we were covering uh, details about buffer pools, and we're going to do a recap on that. So let's do a quick recap that where we started. We started with how pages, databases are just files on disk, and buffer pool serves as a cache for those pages. And so buffer pool is basically a fast storage for your pages which are lying on disk. So then we saw that how the execution engine requests a page, then it gets to the buffer pool asks the storage manager how to find it, then you bring in the page directory to locate that particular page, and then the storage manager just pulls out that page from the disk and puts it into one of your frames in the buffer pools. So we saw all that. Then we also saw that what different type of buffers are there, that you might have special buffers for special queries. Like if you're doing a select star, then you don't want to pollute your main buffers for that. Or if you're doing joins, then you might want to have special buffers for that. Then we also saw that what it basically is a buffer pool, that it's nothing but a large chunk of mallocated bytes, and then on a higher level, on a logical level, you divide that chunk of memory into frames, and then you have a buffer pool manager which manages all the pages. Then you also maintain some metadata in something known as a page table, which lives in memory, which stores information about what page is being accessed and how many queries are referencing that page, uh, and other metadata about that particular page. If like data, like it, if it has been dirtied or not by some query. Is it safe for eviction, or is it like should I write it through, like should I write it back to the disk and assume that my system is in a consistent state? Then we also saw that what are memory map files, that operating systems provide a mechanism to you to map files directly into your process's address space. So if you ask the operating system to map a particular file, the operating system will put that file into your process's address space. And when you read or write to those addresses, it is just as if you were writing to some memory location, but behind the scenes, it is being written to the file. Then you have replacement policies. We were discussing about replacement policies, that so buffer pool is a limited storage. You have limited frames in the buffer pool, and you bring in pages and put it in the buffer pool. And so your physical RAM is limited, and since your buffer pool lives in the physical RAM, you have your limited space for the buffer pool, and there might be some other programs which you might be running on your system apart from the database system itself. So they might be consuming some sort of RAM. So you don't have infinite storage for buffer pool. So eventually, if you want to bring pages in, you might run out of frames. So what you want to do is you want to make some kind of eviction algorithm that efficiently knows that what pages are not being used, and just throw them back out to the disk, and keep the hot pages or the popular pages in the buffer pool itself. So we were discussing about page policies. So we'll go to that, page replacement policies. Last time we covered LRUs, the least recently used, and so last time I was thinking, yeah. So last time I mentioned FIFO, that if you ask a first year CS student that what is the basic cache algorithm that you can think of. So not like I missed last in first out also, and I also mentioned that stack is a FIFO. So I would like to make that correction, that stack is not a FIFO, it's a last in first out. So the last thing you put in is the first time to come out. So like stack, like if you stack books and you want to get the book at the bottom, so an orderly way to do that would be to unstack it. So remove the very first thing, the last book that you kept on top. So that is last in, and that is the first one to be pulled out. Anyways, that was a correction on my part. And so in the least recently used, we saw that there is a linked list, and you maintain some order in this linked list, that whenever a page is accessed, you move that page to the front of the linked list, and uh, the eventual goal of this algorithm is that eventually the page that is lying to the end of the list will be the page that has been not used most recently. So assume that one page has not been used for a period of 2 days. So that page will be lying at the end of the disk and sorry, end of the list, and that page you'll pull out and throw back out to the disk. So we saw through. Then we also saw the clock algorithm. So we also corrected some mistakes in this, that initially all the reference bits are set to 0, and the page, whenever the clock rotates, the hand rotates, it finds the first page with the reference bit 0 and just throws it out. So whenever a query references a page, it resets the reference bit to 1. And the next time the clock algorithm runs, and if it sees that there is a reference bit 1, it sets it to 0 and moves on. So the very first page that it finds with the reference bit 0, it throws that out. But if any of the pages that have the reference bit as 1 along the walk path, it will set that reference bit back to 0. So that's what we saw. Like you can look here. So this page had reference bit as 0, 1, and the clock set it back to 0, and then it just moved on to the page 2. The page 2 was, if you cannot see, so page 2 was reference bit 0, and it decided to throw it out. This is what Linux uses also for their maintaining their eviction policy in down in the buffer, down in the page cache of the OS. So we saw that. Then we also talked about sequential flooding, that LRU and the clock algorithm are susceptible to something known as a sequential flooding. What is sequential flooding? Sequential flooding, you do a select star on some table without any index, and you bring in a bunch of pages, and those bunch of pages pollute your buffer pool. And what can happen is that some query comes along and it brings in a bunch of pages. So like there is this, assume that this particular Q1 is a uh, very popular flow path of your application, and this query is being executed again and again. And what it does is, let's say this ID belongs to Taylor Swift or something. That that's the example Andy gave, that this belongs to Swift's account. So people come in and they keep hitting this query. But some other query comes along. Maybe you're doing analytics in the background on your offices and and you want to calculate some average value. So this query comes along. It wants to do a full table scan. So what it will do is it will go around touching a bunch of pages from 0, 1, 2, and 3. And what will happen is that it will bring page 3 in. So 0, 1, and 2 are already in the buffer pool. But as soon as it says that I want to bring page 3 in, it will throw out page 0. So what you did here was, due to one query that you're doing a sequential scan, you are bringing in pages one by one, but you are also throwing out essential pages, which might be useful on your hot paths, or which might be useful for majority of your queries. So let's say again a identical query to Q1 shows up, which is Q3. So again it is on your hot path. Let's say Taylor Swift's Twitter account, and so it comes along and it tries to read the same data, but it sees that it belongs to like, we're not saying that how we got there, but let's say it knows that that particular thing is in page 0. So, but it would have been beneficial if page 0 was in memory, but it is not, because it was thrown out by that sequential flooding, like the sequential scan that was the above statement was doing. So these sequential statements, the sequential scans on full table, the whole table, can pollute your buffer pools. So yeah, that's where we left off last time, and now we will start with the next algorithm. So what we'll do in this video is we'll cover LFU, LRU-K, Then we'll cover LRU approximate LRU. Yes, MySQL uses this approximate LRU-K, and I think LRU-K is used by MS SQL, Microsoft. Yes, Microsoft SQL Server uses LRU-K, and MySQL uses approximate LRU-K. So after that, we'll talk about Arc. Arc, I was studying about this uh, yesterday, that how this works, and uh, the working is very close to what the name represents. That the cache adapts itself. So yeah, we'll talk about this also. So let's talk about LFU. So LFU, as it says, least frequently used. So in the least recently used, you had the notion of time, that you were maintaining pages based on when they were used, when they were used. In least frequently used, you have the notion of the number of accesses. You are tracking pages based on how many times that page has been used. But if you pause this video and if you think about it, then inherently that has a problem, because let's talk about a scenario. Let's say I wake up one morning and I decide that I want to maybe open some random Instagram account. Assume that we have a small Instagram clone, and I wake up and I decide that I want to watch all the videos of a particular Instagram account. Sorry, and that particular Instagram has a ton of videos. So I go ahead and I bring that page in, and I access that page, let's say over 1,000 times. But then nobody else is interested in that account except me. But my only access my the only accesses that I did has the frequency count increased to 1,000. So that particular page of that particular Instagram account will never be used again, because I've gone back to sleep and nobody else is interested. But that particular page has a high frequency count. So according to this algorithm, that page is useful. So it might linger on in the buffer pool for a long period of time. So the another problem with that is so we'll just read through to identify popular pages, maintain an access count for each page, and then evict the page with the lowest count. Uh, the second point, uh, the second point says that what I just explained, that ignores time and accumulates stale pages. So stale pages might get accumulated in your buffer pool, that uh, some particular instance a page was used very heavily, but then it is not supposed to be used for a week, but due to your algorithm, that page still might be retained by the buffer pool for a long period of time. The very first thing is the implementation complexity. That we said that we are maintaining access counts for pages, but when we need to evict, we also need to find the maximum, the minimum, the page which has the minimum number of accesses. So what is that? That is, if you might loop over all the pages, that is an O of n operation. But you are maintaining some structure like uh, a heap, a priority queue of sorts, then you might reduce that to logarithmic, but it's still some overhead of maintaining that order structure of what is the minimum accessed page. So LFU is right out of the window. So this is just for telling you that this exists, but nobody uses this alone. This is not used alone, but it gives good estimates of uh, how many times this page was particularly accessed. So let's talk about LRU-K. So what LRU-K does is, in LRU, we were just maintaining a linked list, and as pages were being accessed, we were moving pages to the front of the list, and slowly with time, they were traversing their way back to the tail of the list. What we do in LRU-K is we maintain K number of accesses. we maintain k number of timestamps for the page that we are maintaining. Let's say k is 2. So what we do is for a given page, say page 1, we maintain two timestamps as to when they were accessed. If the page was not accessed, these are by default infinity. If the page was accessed, then you fill in the values. Then, while evicting an page, what do? You take the current timestamp of the system. That a timestamp might be some incremental counter you are dealing with, or you might use the wall clock time. Usually, systems don't use the wall clock time, but it is some internal counter that is being incremented, and you take that timestamp and you subtract the kth access time, and you evict the page with the largest difference. So, what LRU-K tries to achieve is that it tries to strike a balance between recency and the frequency of access. That with timestamps, you are giving some sense as to when page was accessed, and with maintaining K number of timestamps, you are giving some sense as to how many times this page was accessed. So let's think about it in two dimensions. That here, page 1, page 2, T1, T2, T3. Now, these particular columns, individually, these columns are telling me that how many times the page was accessed. And the data points in these is giving me some sort of estimates about when this page was accessed. So LRU-K tries to achieve what LFU and LRU could not do alone. We'll talk about that. We'll talk about ARC. That also does something similar, that it maintains a LFU cache and a LRU cache, and it tries to give you some estimate as to it adapts according to different scenarios. We'll talk about that. So there's also a ghost cache, as we read that a ghost cache is basically some information about the pages that have been thrown out. So assume that you have some pages and you're maintaining some metadata about that. So wait, Andy has slides about this. Okay, so this is a walkthrough. Okay, let's do a walkthrough. So what is a ghost page? Theoretically, a ghost page, ghost cache is just metadata about the pages that you did have in your cache, but they were thrown out, but you did not throw out their metadata, that you didn't throw out their timestamps or any other information that you had. So when you bring that page back in, you might want to reuse that information about the page. So if you're bringing a page that was familiar to you, you do not start from scratch for that page. You have some sense of when it was accessed, and to just not start from scratch for that page. So let's do a walkthrough. So assume that you have these three pages in memory, starting in the base scenario, that you have these page 0, page 1, and page 2 in memory, and you have the k is set to 2 here. Yeah, it's not written anywhere, but the k is set to 2. So let's say k is equals to 2. So we have two timestamps, and time 1, time 2, and time 3. These are the timestamps when this page was particularly accessed. Query one comes along, it reads page 2, and let's say this was before Q1. This was before Q1. So now Q1 comes along and it reads page 0. So what page 0 does is, page 0 was accessed by Q1, so it will put its timestamp 4. In this scenario, current time is 4. Timestamp is 4. So again, time is not a wall clock time. You might use some internal counter for time as well to give you some sense of when this page was accessed. And that is as good as, yeah, that's a philosophical discussion. But anyways, uh, so at this starting point, K was 2 and timestamp was at 4. So at timestamp 4, Q1 shows up and it accesses page 0. So it accesses page 0 and it tells that last access time was timestamp 4. As I said, that empty blocks are infinity, are set to infinity by default. Okay, so remember that. So we have Q1 again, and it wants to touch page 3, but we don't have space in above pool. So what do you want to do? You want to go along all the pages, take their kth timestamp. K is 2 here, remember. So we go and we read this particular column. This is infinity, this is infinity. Now current timestamp is 5, 5, and now we subtract. 5 minus 1 is 4. Infinity minus 5 is, you can do it either way, but usually it will go to minus infinity, but you understand the point, right? So you evict the page that has the maximum distance, maximum absolute distance. So even if you do a minus infinity here, so the absolute distance would be infinity itself. So you evict the page which has the maximum absolute distance. So apart from that, this is a tie. How do you resolve ties? You look one step back. You look at the k minus 1 axis. So now if I subtract this from 5, 5 minus 2 is 3 and 5 minus that's 2. So which page do you evict? You evict the page 1. Why? Because the last, okay, so we started with the kth axis. Then we found out that which pages are the candidates for eviction, which might, you might also have resolved the conflict in the kth column itself. But since we had two rows with the same distance, then what we did, we jumped back. We jumped back to the k minus 1 block and we read those timestamps. Then we subtracted them and then we found out the maximum distance in that. And that came out to be page 1. So page 1 is our candidate and we evict this page. So this is eviction policy, current timestamp minus the kth last access time. So current timestamp was 5. So time is 5. That's what the slide shows. 5 minus 1 is 4, and then this puts to infinity. Infinity minus 5 is infinity, and this goes to infinity. So now these two are in tie. So when how do you resolve ties? You take one step back and sorry, you take one step back and then you start subtracting. That will be 3 and that will be 2. So you pick the page 1 and you replace the page 1. That's it. But now also remember about the ghost list. So we had some information about page 1. That is last access time was time 2. We will not throw that out. The ghost cache will maintain this particular timestamp. So when you load that page 1 back in, you can put that timestamp back. So there might be, yes. So assume that this query now wants to read page 1. It will go do the same thing again, that it will go through. Let's walk through again. We are at timestamp 6. This goes to 5, this goes to infinity, this goes to infinity, and these two are in tie. So what we do, we jump back and we calculate the distance. This is 1, this is 3. So page 2 is our candidate for eviction. So we throw this page out now. We throw page 2 out. We throw page 2 out, we bring page 1 in, which is query needed. But look at this now. We have timestamp 6. This is our current timestamp. But we also have timestamp 2. Where did that come from? That came from the ghost cache we have. So the ghost cache is basically your starting point for any pages that you might have seen in the past. Uh, yeah. So this is it, and so let's do. There's more of it. Let's walk through. So we have page 1 again. Let's say the query wants to read page 4. So page 4, there is no space in the buffer pool. What it will do is it will start looking at the current time. Time is 7. Difference is 6. The difference is 5. Difference is infinity. So now this is obviously the candidate timestamp 3. So it gets thrown out. Timestamp 3 is thrown out, timestamp 4 is brought in, but the information about timestamp 3 is still stored in the ghost cache. So that's LRU-K. This is a beautiful algorithm. It gives you some sense of how recently that page was being used and how frequently that page was being used. So it tries to balance between the LRU and the LFU. Then we have approximate LRU-K. Now, this is a similar idea, but rather than maintaining timestamps for your pages, you maintain a linked list and you divide that linked list into old and young sections. So if you might have studied about garbage collectors, some garbage collectors use this concept, like I guess JVM's Java's garbage collector maintains this region of the old objects and young objects because it is highly likely that the young objects are easily to be killed and garbage collected, while the old like long-standing objects are less likely uh, to be garbage collected. Okay, so that's the yeah. So that was LRUK. Now we'll jump to approximate LRUK. So what it does is it divides the same list you had in LRU. You divide that list into two parts. One is the old part and one is the young part. And when you have to evict, you take the last element of the old part. So the old list at the end is at the end, and you maintain the young list at the start. Although when I was studying this, I assumed that the old part was the pages which are less likely to be evicted, but that's not the case. The old list contains the pages which have the pages which are most likely to be evicted. So the new pages are always inserted to the head of the old list. So if they're not used, they will eventually slide down to the end of the list. If the pages in the old list is accessed again, then insert into the head of the young list. So if you are using this particular page again, so you jump this page above the hierarchy. And the eventual goal is that you will somehow just maintain some ordering as to when this page was used and how frequently it was being used. So let's say we have this particular structure here, and let's say some query comes along and wants to access page one. So the page one is not there. So what you do, yes. So I thought they would pick up the wrong thing. But what do? You go to the old list, you scrap it, and you insert this page one to the head of the old list. So now it will be page one and page six. Now, if this query comes along again, let's say some other query comes along with Q2 and it wants to access page one again. It accesses it, but the algorithm at the same time moves this page to the head of the young list right here. So now this page three comes to the old section that it is old. Yeah, so now that I'm speaking of it, it also makes sense actually that old pages are old. So they have not been used in a long time. Like if you have an old car, it might be that it has not been used for a long time. So yeah, that makes sense actually. And the young list is that recently have been used. So that was approximate LRUK. Next we have ARC, the adaptive replacement policy cache, adaptive replacement cache, and we'll talk about this next time. I'm doing these short videos, but I think I'm gonna have to maintain some consistency for this, else this 25 lecture, uh, like this is a composition of 25 lectures, right? And we have just reached the fourth one here. So I don't want to take all year delivering these. So maybe let's see. Thank you for watching.